Okay. So, good morning to everyone. First of all, let me thank you, Chancellor Saab, Professor Sayyid Wasim Akhtar Saab, Pro Chancellor Dr. Sayyid Nadeem Akhtar, Vice Chancellor Professor Javed Musarraf Sahab, and Dean Faculty of Science Professor Abdul Rahman Khan to allow us to organize the expert lecture. So it is my honor to introduce the distinguished speaker, Professor Maxim U. Khlopov. He is the director of Center for Cosmoparticle Physics, National Research Nuclear University, Moscow, Russia. He was also the director of Virtual Institute of Astroparticle Physics, APC Laboratory, Paris, France. Professor Maxim obtained his education from Russia and he has professional history. In 1977, he was the research scientist in Kalish Institute of Applied Mathematics, Moscow, Russia. In 1991, he was the full professor of National Research Nuclear University, Russia. Since 1992, he was the director of Center for Cosmoparticle Physics, Cosmion, and from 2002 to 2004, he was the full professor in University La Sapienza, Italy. Since 2007, he was the director of Virtual Institute of Astroparticle Physics, Paris, France. He got many awards. In 1992, he got grant of Federal Program of Fundamental Research from Russia. In 1989, he got the grant for international project from Italy. Again in 1993, there was a joint project between Russia and Italy. In 1996, he got the grant for international project from Switzerland. He is the member of Russian Gravitational Society and Astronomical Council of Russian Academy of Sciences. His area of research are cosmology and particle physics beyond the standard model, physics of very early universe, primordial black holes, particle physics of dark matter. He has more than 300 research papers to his credit, and the citations are 14,255. His H index 60. Professor Maxim wrote around 25 books, and he is also the editor of International Journal of Modern Physics D. Professor Maxim visited several countries like USA, Poland, Hungary, Germany, France, Japan, Italy, Switzerland, Spain, and many more. So I feel extremely glad to welcome everyone for the lecture. I would also like to thank the organizing team for such a beautiful event. I assure you that this event will be an immense success and a boon for all the participants. So let me invite Professor Maxim to deliver the invited lecture. Please, sir.
Thank you very much for a possibility to share with you the some flavor of science which I'm doing for more than 50 years. Hopefully now you see my slides. It's cosmoparticle physics. It's a science about fundamental relationship of cosmology and particle physics in general. It is the final level of traditional correspondence between microscopic and macroscopic description of physical phenomena. And here we take the extremes of our knowledge in micro world and macro world. And I'd like to give you some ideas why we should, what is the standard model, why we should go beyond it in physics, that this beyond the standard model physics, it just is physics of modern cosmological paradigm, and my aim is to show that in this approach, inevitably, something that goes beyond this standard model cosmological paradigm should come. And I'd like to discuss few examples of these exotic phenomena, like dark atoms of dark matter, like primordial black holes, and strong primordial non-homogeneities in inflationary universe, as well as with non-homogeneities, maybe either non-homogeneities of energy density or non-homogeneity of baryonic charge, so that the same mechanism which creates us the existing baryonic matter in some places can provide us existence of antimatter and antimatter stars in our galaxies. So the standard model of particle physics extends the gauge principle of quantum electrodynamics, and just it led to now standard SU3 for quantum chromodynamics and SU2 cross U1 symmetry of electroweak interaction. And this symmetry just is accomplished by Higgs mechanism of spontaneous symmetry breaking, which explains the difference between weak and electromagnetic interaction. The, however, this this standard model assumes that we have three families of quarks and leptons, and it just mm, experimental data. Moreover, all the elements of these constructions, all the quarks and leptons, as well as Higgs boson, are discovered in the accelerator and collider experiments. But there are many problems of this standard model which make us to think about its extension and modification. So actually, these problems are related with excessive number of parameters of standard model. Actually, we put, for example, for each mass of each quark or lepton, we put the parameter which corresponds to measured value. So there is no prediction of mass. And there's the problem of neutrino mass, which is much smaller than mass of charged particles, and so on. There is a problem of strong CP violation in QCD, which implies extension of the standard model by additional symmetry. And there is the problem of divergence of Higgs boson mass. And these two phenomena led to such popular ideas of axion and axion-like physics in the first case, and supersymmetry in the second case. So there are statistical arguments which also just appeal to unification of all the forces in the framework of grand unification. And this there is a necessity to give theoretical explanation is much smaller than mass of the corresponding charged lepton, and it leads to so-called seesaw mechanism of generation of neutrino mass, which may lead to lepton number violation at such exotic processes as neutrinoless double beta decay. The fact that parity is not conserved in weak interaction made first Lee and Young, and then by Kobzarev, Hock, and Pomeranchuk, to think that in order to restore symmetry between left and right-handed coordinate system, we need mirror partners of ordinary particles, as well as mirror partners of their interactions. There is an idea that we can embed the symmetry of the standard model within the SU5 grand unification, which involves inevitably existence of gauge bosons which lead to proton decay. The Experimental data, however, show that this minimal extension of unification is not sufficient because the predicted lifetime of proton appears to be contradicting with lower limits. And it makes us to consider more extensive grand unified models. There is this symmetry between families, and this family symmetry just is evidently broken by the hierarchy of neutrino, quark and lepton family masses. So this broken symmetry can lead to creation of to existence of number Goldstone bosons familions. To solve the problem of strong CPU violation, additional symmetry proposed by Pichet Queen should be involved, and its breaking just leads to existence of number Goldstone boson, which we call axion. To explain the electroweak symmetry scale and to solve the problem of Higgs boson divergence, we should assume that virtual processes with ordinary quarks particles should be cancelled by the corresponding loops of supersymmetric partners, which have different statistics, so that fermions have boson partners, while bosons have fermion partners. And so the difference in statistics of Fermi-Dirac and boson lead to cancellation of the corresponding loop contributions. And it explains in this approach why there is no divergence of Higgs boson mass. Moreover, this approach can lead to unification of all the four interactions in the framework of supergravity. And we can go also beyond the standard model for dimensional space-time and consider the extra dimensions, which may be either compact or infinite, and the generalization of all these approaches in string models lead to superstring heterotic string models in which you can, in principle, have a hope not only to embed the divergences into the finite number of measured values, as it is in quantum electrodynamics and all these models of renormalization. But it is possible to have finite theory, but still the problem here comes from the very huge extension of symmetry of standard model, which is accompanied by multidimensional space-time, by very high gauge symmetry, and so on. So actually, in order to prove this approach, we need some extensive way and methods to study it in all the details. However, we have very few experimental ways to do it, like proton decay, like search for some exotic processes in which lepton or baryon number is not conserved, to look for some exotic decay modes. So in that sense, we need to extend the way to prove a new physics. And in general, expanding universe was considered as the proper tool for that, because in expanding universe we have very early Big Bang period in which, in principle, the energies which we have to reach with high effort at the collider were naturally realized in natural conditions of very early universe. However, the problem is that we want to probe unknown physics by cosmology and find that 95% of energy density of universe corresponds to something what we don't know. And it makes us to make the self-consistent treatment of cosmology based on three important elements: inflation, baryosynthesis, and dark matter and dark energy. And inflation, baryosynthesis, and dark matter just should be described by new physics, which we would like to study with the use of cosmological probes. So the idea of cosmoparticle physics is to combine all the physical, astrophysical, and cosmological consequences of new physics so that you get overdetermined system of equations relative to unknown parameters. It means that you have much more equations than number of parameters, so the set of equations can be either fulfilled or just you can rule out this approach. For cosmological consequences, the most fundamental properties of particle world are important, because to be candidate of dark matter, you need something what is sufficiently long living, and it means that there is some conservation law which prohibits particle decay. Another point is that symmetry breaking involves in early universe but just a restoration of particle symmetry, so the transition from symmetric to asymmetric phase can be accompanied by topological defects which may be either stable or unstable. Uh, our paradigm of formation of logical structure assumes that you have homogeneous and isotropic universe in which you have small density fluctuations. And in order to make this fluctuation to grow up to the observed structure, we need dark matter, because for long period before recombination, baryonic matter is ionized and experiences pressure of radiation, which converts density fluctuations in sound waves, and they don't grow. So in order to trigger and support gravitational instability and formation of observed gravitationally bound object from slow growth of density fluctuations, we need something what is decoupled from matter and radiation, and this is the main role of dark matter. Actually, it reflects just the most important features of particle models, because it involves extension of particle symmetry, and really all the candidates for dark matter reflect such new symmetry. In principle, the most simple and natural for last 3 decades candidate for dark matter was so-called WIMP, weak interacting massive particles. And it was really a miracle that if such particles have few hundred GeV mass and annihilation cross-section of the order of weak interaction, their energy density now can explain the dark matter density. Moreover, in supersymmetric models, lighter supersymmetric particles should have behaved like WIMP. And so there was a great hope that simultaneously we should discover WIMPs and we should discover supersymmetric partners at the LHC. However, the results of this search is for the moment negative, and it makes us to consider more wider class of different model candidates for dark matter, which follow from different necessary or important extensions of symmetry of standard model. Actually, existence of beams can be proved experimentally because weakly interacting massive particles can cross terrestrial matter and in underground detectors cause a recoil. And if we combine this recoil with effects of annual modulation, then it may possible to find in a way in which you can strongly suppress any background effect of this dark matter. And the paradox of the experimental results looks like that, because there are positive results with high confidence level. Now it is nearly 13 standard deviations in Dama sodium iodine and Dama Libra experiment, and attempts to find WIMPs in other experimental groups. Actually, this puzzle may simply follow from the fact that in the same way as as ordinary matter consists of neutral atoms in which electrically charged nuclei and electrons abound, in the same way, dark matter may also be have charged constituents which are hidden in dark atoms. So actually, the main problem here is to avoid overproduction of anomalous isotopes, because if you have some new heavy particles with charge +1, it binds with ordinary electron and forms anomalous isotope of hydrogen, which is excluded as very high, with very high precision in the terrestrial matter. So actually, it means that only particles with -2n charge can be possible to consider, and they do not lead to immediate contradiction with existence of dark of absence of anomalous isotopes. So the interesting feature of such case is that atom of this type looks very unusual, because instead of ordinary atomic physics, where we have small nucleus which has strong interactions and large Bohr orbit which is much larger than the size of nucleus, here we have lepton-like negatively charged particles around which helium nucleus just rotates at the Bohr orbit, which is nearly equal to the size of helium. So all the natural assumptions and approximations which are possible in atomic physics, in dark atomic physics, cannot be used, and we need some methods to elaborate the physics of such dark atoms. There are several examples from theories which can not only provide us existence of such multiple charged particles, but can relate, in case of working technicolor, there is a balance between excess of baryons and excess of new stable particles, so that actually we can reproduce the observed dark matter density in this scenario by a simultaneous creation of baryon excess and excess of these negatively charged particles. Uh, These particles may be not only a double charge, but they may be multiple charge. And then we have a situation which is very unusual, because it's not Bohr atom. It is Thomson-like atom, in which -2n charged lepton is within the n alpha particle nucleus. So actually, we are now on the way to develop the physical description of this scenario, but it leads to natural possibility that in spite of strong nuclear interaction of these objects, they lose primordial gas of these dark atoms, decouples from plasma and radiation, and plays the role of dark matter. And in the Earth, these dark atoms, when they fall down the terrestrial net, they move towards the center of the galaxy and center of Earth. And in underground experiments, it simply means that at each level there is a equilibrium amount of these dark atoms, and their interaction with matter of detector can explain annual modulations in inelastic processes by which dark atoms bind with the nuclei of the detector. So that actually then nucleus of this detector approaches dark atoms. Then first there is polarization of dark atom, which attracts nucleus, but at some moment that nuclear attraction makes helium to be between negatively charged component and approaching nucleus, so that there is it repels it, and this repulsion can lead to the just a moment. Okay, so actually, this repulsion can create a barrier with which we can explain existence of low energy bound state between nucleus and dark atoms. It can reproduce, in fact, by analogy with radiation capture of neutron, we can reproduce the rate of such processes together with number of events, and it corresponds to what Dama sodium iodine and Dama Libre experiment does observe. The main problem here is the potential barrier, because when we consider this stage, here any perturbation methods don't work, and so now we are involved in very complicated numerical analysis of this problem. So actually, the situation with probes for such dark matter scenarios strongly differs from what people now describe in complementarity of different probes for dark matter candidates. Because at colliders, the idea is that you should look for missing energy and missing momentum carried by weakly interacting particles. In case of dark atoms, we should look for multiple charged particles, and such experimental search at the LHC just puts a lower limit on the mass of these particles. So actually, one of the important feature of our universe is that it is homogeneous and isotropic. However, if there was a possibility to stop expansion in the within the cosmological horizon, then you may form black hole which may have arbitrary mass as compared with dark black holes which appear in the result of stellar evolution. And there are constraints on such primordial black holes of different masses. And for a long time, primordial black holes were considered as something that doesn't exist, but constraints on them could put some probe for early universe. For example, primordial black hole probability of formation was strongly dependent on the equation of state of early universe and can probe existence of early matter dominance, as well as it may be indicator of first order phase transitions in which false vacuum bags can convert into the black hole. And Hawking has found that actually small mass black holes should radiate, and the important feature of primordial black hole evaporation is that it is a fact of strong gravitational field near the horizon of black hole, so that anything what may be present in our space-time can be created in this way. So however super weakly interacting particles we assume, they should be produced numerously in this process of a primordial black hole evaporation. If the mass is larger than 10 to 15 grams, this effect doesn't prevent them to exist now and to be some non-trivial form of dark matter. And here we come to the general question. How can we accept existence of strong primordial non-homogeneities in a homogeneous and isotropic world? The idea is that in principle it is possible if we have some tiny component which contributes very tiny in the total density, but is strongly non-homogeneous within itself, so that there is no contradiction between general homogeneity and isotropy of the universe. And there are two different types of strong primordial non-homogeneities. It is non-homogeneities of energy density, like in extreme case it is black hole, or some non-homogeneous structures of dark matter, or it may be non-homogeneity of baryosynthesis, so that in an extreme case, non-homogeneity of baryosynthesis can lead to a negative sign of baryon excess, so that baryonic matter can be accompanied by regions of antimatter, so that antimatter domains can appear in baryon asymmetrical universe. Actually, at large temperatures, we can have phase transition, which corresponds to the change of symmetric case, which is restored at high temperatures, so that you don't have a minimum at non-zero vacuum expectation value of the Higgs field, so that you have a transition at some critical temperature. If you have a chaotic inflationary scenario, then inflaton can interact in the same manner with Higgs field, so that at early stages of inflation you can have a restoration of the symmetry, and when it is broken, then the inflaton moves down to the its true vacuum. So when you have such a phase transition, depending on the symmetry of broken symmetry phase, you may have, if there is a discrete symmetry, it may be plus or minus vacuum expectation values, so that there may be domains of true vacuum with plus and minus. And there should be border, and in this border you have false vacuum because you have continuous transition from a plus to minus. If you have continuous degeneracy, then you have a geometrical place of such singular points in which you cannot determine this phase, which corresponds to cosmic string. And if you have SU2 degeneracy, it is the case of singular points which share properties of magnetic monopoles and its general feature of grand unification. So actually, axion-like particle model in which you have two scales at which one scale corresponds to the vacuum expectation value of the amplitude of the complex field, and the second just determines the uh, energy density corresponding to the phase which acquires meaning of field. And it's just what happens in axion models. If the first phase transition takes place after inflation in the Big Bang case, then you have first cosmic string, and then at the second step, this Mexican hat is tilted so that you have only 0 and 2 pi true vacuum, and it leads to the structures which appear in this case in the form of unstable topological defects when you have cosmic string which walls between different cosmic strings. The structure is unstable, it decays, but the surrounding energy density distribution of axion-like particle field just retains it, and so that you have what we call archival structure, so that you have large-scale correlation in such strong non-homogeneity. If you have phase transition at inflationary stage, then the phase is fixed for all the observed part of the universe. But then at next steps of inflation, you may fluctuate this value of phase. So in some regions, you can cross pi, and with the second phase transition, then you should go either to 0 or to pi. You have dominantly in the universe the value 0, but there are some closed regions in which you have true vacuum of order of 2 pi. And in this case, you have a set of closed walls, and these closed walls, if they collapse, they reproduce, they can create black hole clusters, and the masses of black holes are determined by these two fundamental parameters of the model, because if in order to create black hole, you should put all the mass of the closed wall within gravitational radius of the corresponding mass, and it leads to minimal estimation, minimal mass of black hole. However, if the mass of closed wall is too large, and the wall is too large so that it dominates before it enters horizon as a whole, the regions in which it starts to dominate experience superluminal expansion, so that you have a wormhole which finally just separates as a baby universe. Actually, it is in these processes of such collapse, you should expect gravitational wave effects, and in particular, clustering of black holes can explain, for example, results of gravitational wave experiments. However, now we have experimental indication that there is a stochastic gravitational wave background, and we found that simultaneously in axion-like particle model, it is possible both to explain the gravitational wave background by the effect of closed wall separation and baby universe creation. However, in order to create such black hole, you should such a wall, you should approach pi from the value which is averaged for all the universe. So you have increased the amplitude of oscillations of axion-like particle field. So simultaneously with stochastic gravitational background, we predict primordial non-homogeneity of dark matter, so that early galaxy formation observed by the James Webb Space Telescope can be explained. And here I give just the general description of different approaches to probe axion-like particle physics. Now let me come to the final topic of my discussion. It is the question about antimatter in baryon asymmetric universe. It reflects strong non-homogeneity of baryon excess. Moreover, in order to survive in the surrounding of matter, antimatter domain should be sufficiently large, and the minimal value of their mass corresponds to something like 1,000 solar masses. In spontaneous baryosynthesis, it is possible, in the same way as we discussed in axion-like particle models, it is possible to explain existence of antimatter in baryon asymmetric universe, so that nearly each galaxy may have antimatter component which just corresponds to mass of globular cluster, which can lose its antimatter, annihilate, and it should give to gamma ray background, which may be reproduced in this way. But it's not the proof for antimatter. For a proof of antimatter is existence of some pieces of antinuclei. We can create them in laboratory, but in space it's strongly improbable. Therefore, if IMS experiment can find something, then it cannot be from astrophysical sources. It should be from primordial antimatter component of the universe. So it's strictly confidential, it's not published. However, 5 years ago, some team presenting results of his experiment have shown an event which looks like anti-helium. 5 years later, this year, he demonstrated this effect. 5 years ago, he said, well, there is probability of 1 to 300 that it is background event. So now he claims that there is no possible background explanation of this result. However, they don't publish it because they are the only group which can, in principle, reach such sensitivity in search for antinuclide, and it makes them very highly responsible for publication of their result. The experiment is continued until 2028, and it can provide increase of statistics and reject possible backgrounds, so that the result, whether the anti-helium-4 component does exist or not in the cosmic rays, will be proved. So we come to conclusions that physical basis of modern cosmology implies new physics. And here we see that the dark atom hypothesis can explain puzzles of direct dark matter searches. Primordial black holes can probe physics of very early universe, and we have physical mechanisms of a region for primordial nonlinear structure. It reflects general and basic ideas of cosmoparticle physics, which approaches new physics scale from different complementary parts. So that in particle physics, we normally come from relatively small values of this scale. However, in cosmology, it can be probed if it is close to Planck scales. And in astrophysics, we can have effects which are in the middle. So combining all of them, we come out of the vicious circle of problems, because if we start from particle physics, we want to probe it by cosmology, but cosmology needs just that new physics which you want to probe. So the principle which I have tried to illustrate today is that any model of inflation, baryosynthesis, and dark matter contains some model-dependent, non-trivial cosmological consequences, which move cosmological scenario from beyond the standard cosmological paradigm, so that these unusual phenomena can provide us sensitive probe for new physics. Moreover, if we have positive indication for existence of these processes, then you can just rule out most of theoretical models which do not explain it, and you concentrate on the cases which can predict these exotic phenomena, which, if they are observed. So I just can recommend you my books on this subject. Just studying different at different languages, just some different aspects of fundamental relationship of micro and macro world, and we support activity of collaborative works of the um, online participation in different conferences, online support of conferences, as well as collaborative work on in my virtual institute of astroparticle physics. So now I thank you for just attention.
So thank you so much, Professor Maxim, for this wonderful talk. And we have some questions from the students.
Yes.
So there is a one question from the students on the screen. So can you see at your
Yes,
screen?
are sterile neutrino totally different from the already free known neutrinos? Yes, by definition, because they're sterile. It means that they don't share weak interactions, which are the only fundamental interaction for neutrino for known neutrinos. So sterile neutrinos, by definition, don't have ordinary weak interaction, unless there are some processes of mixing with ordinary. But by construction, stellar neutrinos should be different. You have another possibility of Majorana mass. Then you don't need right-handed neutrino to explain mass of neutrino. But in this case, you violate lepton number conservation, so that neutrino and anti-neutrino are different states of one massive neutrino, but in this case, you can avoid the necessity to involve new states of neutrino. How does the interplay between the standard model of particle physics and cosmological observation shape our understanding of fundamental laws governing the universe? Uh, Actually, when you try to probe new physics, which we need to explain cosmological structure, the structure and evolution of the universe, uh, we involve physics which is beyond the reach of experimental facilities like a collider or natural astrophysical sources of super high energy cosmic rays. So, in that sense, we need some complementary information, and cosmological proof provides us with possibility. The basic thing here is that you just add the number of equations relative to unknown parameters so that you can fix these parameters and either prove or rule out the corresponding model of fundamental laws governing the universe. That's the idea. What are the implications of high-energy particle experiments? Now, understand your early universe and its fundamental processes. Well, there are several widely known possibilities which are related with, for example, reproduction of early universe hadronic plasma, uh, and then you just uh, and as well as in cosmology, uh, you don't know the name of particle. You know its general properties. However, in experiment, you specify these properties, so it is something complementary. Moreover, there is another thing. You assume something, what is you need for cosmology. And then it turns out that in order to fix parameters of your cosmological scenario, you need some additional data which you don't know, which in general doesn't look of a frontier of modern physics. So, one example. When we discussed possible constraints on primordial black holes or antimatter domains and so on, it turns out that antiproton annihilation with helium 4 was not well known. So we, with Yakov Zildovich, just asked experimentalists to measure it, and it was measured at Lear CERN. And the result was that antiproton annihilating with helium-4 creates up to 20% of fragments of tritium and helium-3. And it provided very sensitive probe to possible cosmological consequences of particle physics, which were related with the appearance of antiprotons in early universe, with observed and measured abundance of light elements. And in this logical chain, we just needed some additional element, and this link to this chain was just this experiment in which antiproton helium-4 interaction was studied. So it doesn't look that it is something directly related with supergravity, because one of the sources for antinuclei, antiprotons in early universe were gravitina decay, and gravitina is prediction of supergravity. How do particle interaction during the early universe impact its large-scale structure? Well, good question. It depends on the strength of this cross section of the interaction, because depending on the the simplest relationship between particle properties and large scale structure is that you have some gas of new particles, and these weakly interacting particles, just when they start to be non-relativistic, then just it determines the scale of structure which these particles can form. However, if you have much more elaborated hidden sector, then you may have, so one example. Assume that you have mirror world, and in mirror world you have mirror atoms. So and you have mirror baryons and mirror electrons. So that in mirror world uh, just reproduces large scale structure in a way in which your interaction between uh, mirror electrons and mirror nuclei determines recombination. And this recombination gives the scale at which this structure can be formed. So, depending on the properties of particles, uh, you can have different relationship with large scale structure. In dark atom hypothesis, you also have non-trivial features, because in spite of very high masses of this multiple charged candidates, the bound state possess nuclear interaction, and this nuclear interaction holds dark atom gas in thermal equilibrium with plasma, so that there is some suppression of small-scale fluctuations relative to the standard cold dark matter scenario. So it gives you warmer than cold dark matter scenario.
So thank you so much, Professor Maxim, to give the answers of the questions uh, that were asked by the students. So I also have two questions.
Yes, please.
So, so we know that dark energy causes the acceleration of the universe. So, is there are some experiments or observations to detect the nature of the dark energy?
Good question, because the nature of dark energy, which is dominant relative as we assume in our standard paradigm now, so it's dominant energy density. However, it assumes that you have you need something what drives acceleration of expansion, and uh, in order to uh, prove physical nature of this component, which inevitably should have negative pressure with large absolute value of pressure, then just you have accelerated regime. Uh, there is something what I don't know for the moment, and it's very interesting for me to understand that if you have simple cosmological constant, it means that you have new fundamental constant in physics, such as fundamental as Planck constant, as speed of light, as gravitational constant. So you have some new scale which just is very large in dimension, in length, but in any case, it is something which may cause some non-trivial effects. Moreover, it may not be so simple as cosmological constant. It may be something like quintessence or some exotic form of potential. Well, in principle, any massive scalar field theory gives you inflation acceleration at the stages when you have evolution of this massive scalar field at time scales which are much smaller than frequency of its oscillations. Then just standard field theory gives you negative pressure state equation of state.
Okay,
And
thank you. One more questions.
yeah,
Yeah, so it's related to dark matter.
sorry.
Okay, so at page, yeah, it's the question is related to dark matter.
Yeah.
So at present, still there are some experiments to detect dark matter in the LHC, Large Hadron Collider in Switzerland.
Well, actually, I have demonstrated on one of my slides the general approach of experimental probes for dark matter. If it is weakly interacting massive particles, you simply search for missing mass energy effects in collider processes, because just these weakly interacting particles we are created and escape from the detection. The type, however, as I told, the mm, physics of dark matter may be not necessarily weakly interacting. Even strong in nuclear sense interaction still provides possibility of dark matter. Imagine that neutron is stable, then neutron can behave as dark matter simply because it separates from plasma and radiation, and just plays with rule of dark matter component which is needed to create a logical structure. Moreover, in our galaxy, such strongly interacting component would also behave like collisionless dark matter gas. So, in principle, it means that not only weakly interacting massive particles, but also strongly interacting particles are of interest to probe their existence at collider. And one of the examples I have demonstrated today when I talked about experimental search for multiple charged stable particles. Such multiple charged stable particles can bind with primordial helium to form dark atoms, which may explain puzzles of direct dark matter searches.
So thank you so much for this wonderful talk, and hopefully we'll collaborate uh, some research papers in future. So
Thank you.
let me invite Professor Shamun Ahmad Siddiqui. He is the head of the department in physics.
Thank you very much, Dr. Shah Alam. First of all, I will extend my thanks to our Honorable Chancellor, Professor Wasim Akhtar Sahab, Honorable Pro-Chancellor, Dr. Sayyid Nadeem Akhtar Sahab, and our Honorable Vice Chancellor, Professor Javed Nusrat Sahab, for their continuous guidance and support. I am also thankful to our Dean, Professor A.R. Khan, for providing us all kind of facilities to organize such a beautiful event. And I'm highly thankful to Professor Maxim Khlopov that he explained the relationship between the cosmology and particle physics in a very simple and elegant way, so that the persons who are not working in cosmology can also understand the interplay between the cosmology and particle physics. And I hope that particle physicists will met with success so that they can weave all the four fundamental interactions together in a single picture. So we can reach the theory of everything. So thank you very much, Professor Maxim, again. And I'm also thankful for our students for their presence and their continuous attention. Thank you very much. And I'm also thankful to my dear colleagues also. Thank you, sir.
Thank you very much for organization of this important bridge between us, and just I hope that it is first but not last occasion for our virtual and probably in-person meetings in future. Thank
Sure,
you.
sir. Sure. Thank you very much.